Welcome to an introduction to vector-valued functions. The goals of this video are to define a vector-valued function and also to graph a vector-valued function. A vector-valued function, sometimes called a vector function, is given by a function in this form. The vector-valued function r of t is equal to f of t times a unit vector I plus g of t times a unit vector j, and we can also express this in component form. And this would be for a 2D curve or a plane curve. What I want you to notice here is that for a given value of t, the vector-valued function returns a vector, and function f and function g for a given value of t would return a real numerical value. And for a vector-valued function in R3 or 3D, it would be expressed in a similar way, except now we have the z component expressed by h of t times the unit vector k, or in component form as we see here. The curves produced by vector-valued functions are traced out by the terminal points of the vectors formed by the function values of f, g, and h. To get a better idea of this, let's take a look at a couple graphs. Here we see a plane curve in blue, and in red we are going to see the vectors that trace out this curve from the vector-valued function. Here we're starting at t equals -3, and watch as t increases. The terminal point of this red vector traces out the blue curve, as we see here. So the terminal points of the vectors produced by the vector-valued function creates a curve. Now let's take a look at a space curve generated by a vector-valued function. Again, here we see the vector produced by the vector-valued function in red, and the curve the terminal points produce as the value of t changes. Here we have t equals -8, and as it increases to +8, we see that it traces out the blue curve. One other thing we'll notice about vector-valued function is that the curves are traced out in a specific direction called the orientation. And a lot of times when we're asked to graph a vector-valued function, we need to show the orientation by placing arrows on the curve. Let's take a look at a couple of examples. Here we want to evaluate the vector-valued function for each value of t. Then we want to write an equation for the function in rectangular form and then graph the vector-valued function. So for r of 0, we replace t with 0. So we'd have 0 times the I vector plus -0 squared plus 5 times the j vector. So notice here we'd have 0 times the I vector plus 5 times vector j. So we could express this as 5j, or if we want to express it in component form, it would be 0, 5. This is one vector generated by the vector-valued function, where the terminal point of this vector would be one point on the plane curve. So for r of 2, we would have 2 times I plus -2 squared plus 5 times vector j. Now notice we're not squaring the -2, just the 2. So here we're going to have 2i, and this is going to be plus -4 plus 5, or 1j. Or again, in component form, it would be 2, 1. And for r of -3, we would have -3 times vector I plus, here we'll have -3 squared plus 5 times j. That's going to give us -3i. And here we're going to have -9 plus 5, that'll be -4j. Or in component form, we'd have the vector -3, -4. Okay, for part 2, we want to write this equation in rectangular form. So what we'll first do is write the equation in parametric form, and then eliminate the parameter t, leaving an equation in terms of only x's and y's. Well, here we have the x component, and here we have the y component. So x would be equal to t, and for the y component we have y equals -t squared plus 5. Well, if we need an equation in terms of x and y, and x is equal to t, we can perform substitution into the second equation, replacing t with x. So an equation for this curve in rectangular form would be y equals negative x squared plus 5. In the last part, graph the vector valued function. We'll go ahead and use software for that. We saw it earlier. Here it is again. And again, notice that as t increases, the terminal points of the red vectors produced by the vectored valued functions trace out the blue curve. And again, notice the orientation is from left to right as t increases. Let's go and take a look at one more example. Here we have a space curve because it has an x, y, and z component. We want to evaluate the vector valued function for each value of t again and then graph the function. And again, the main thing to remember here is the output of a vectored valued function will be a vector. So we'll have 2 times cosine 0 times vector I plus 2 times sine 0 times vector j plus 0 times vector k. Well, the cosine of 0 degrees would be 1, so we have 2i. The sine of 0 is 0, so we'd have 0j and 0k, or in component form we would have 2, 0, 0. You normally don't have to express it both ways, but I am just to emphasize the two ways. Next we have t equals pi over 4. Remember, the cosine of pi over 4 and the sine of pi over 4 would be the same. It's going to be square root 2 over 2. Well, 2 times square root 2 over 2, the 2's would simplify, so we're going to have the square root of 2i, and the same for 2 times sine of pi over 4, that's going to be square root 2j, and this will be pi over 4k. Or again, in component form, we would have square root 2, square root 2, and pi over 4. Okay, and lastly we have r of 2 pi over 3. And just to review, let's go ahead and sketch the reference triangle for 2 pi over 3. It's going to be a 60-degree reference angle in the second quadrant. So for the cosine of 2 pi over 3, we're going to have negative 1/2. For the sine of 2 pi over 3, we'll have square root 3 over 2. So let's go ahead and simplify this. We're going to have negative I plus square root 3j plus 2 pi over 3k. Or in component form, we would have negative 1 square root 3 and 2 pi over 3. And we saw that graph of this earlier. Let's go ahead and take a look again. So here we see the vector produced by the vector value function when t is equal to negative 8. And watch as t increases, it'll trace out the space curve. And notice the orientation. So when we evaluated that vector valued function for different values of t, we were finding individual vectors that trace out this curve. Okay, that's going to do it for this introductory video. I hope this gave you a good feel for what vector valued functions are.